for any n that you use that's greater than or equal to 1. So what's 1 factorial? 1. 2 factorial? 2. 3 factorial? 6. 3 times 2 times 1. So, and you could keep going, right? Curious. What is 0 factorial? Well, I told you this formula only works for this, right? For n bigger than or equal to 1. But we actually have a definition of this. And this always bothered me as a student. But this is something where I'm just going to tell you this is what it is, and it's because we've defined it this way. Mathematicians all got together and we said we are going to define this to be 1. Now, if you really are interested in why it's 1, you have to start looking at something later on that involves something called the gamma function, and it's way beyond this class. So if you don't like this, just trust that later on this makes perfect sense to do this, all right? Can you swallow that pill today? Okay. That's a 0 factorial. Pardon?
Is that like important that you want us to start at?
Would I want? Oh yeah, from here on out you need to know that 0 factorial is 1. Because we're going to get 0 factorial later. And when we see it, we're going to put 1. All right? See, 0 factorial doesn't make sense in the definition, right? Because like 5 factorial is 5 times 3 times 2 times 1. Well, 0 factorial should be like 0 to, and then you should get 0 maybe? I don't know. But here, just again, trust me, this is what it is, all right? All right, here's some properties of the factorial. Or maybe we should talk about when you would use a factorial. Like, why would we ever want to use a factorial? Well, what if we have this? Just real world stuff. What if I have, I'm going to pick 3 students out of this class right now, okay? I'm just going to randomly just go to the thing right here. I'm just going to pick a student, and then whoever I pick in first place is going to get an A in the class no matter what. And then the second person I pick is going to get a B, and the third person I pick is going to get an F. All right, now let's see. You know what I'm saying? So how many different ways could this happen? Like, how many different ways could this actually occur? Like, I could pick you, right? A, B, C, yes? But I could also go A, B, C, or I could go A, B, C, or A, B, C, right? How many different ways can that happen? Well, let's talk about the first, when I pick that first person, how many ways can that happen? Well, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There's 20 of us in here, I think. Did someone walk out? They're gone. They get an F no matter what. Okay. So there's 20 of us in here. So I could pick one of 20 people there, right? And then what about the next person? Well, there's only 19 left to choose from, right? So there's 19. And then what about the next person? There's only 18, right? So if I multiply 20 times 19 times 18, that's how many ways it could happen. So that, whatever that is, right? Yes? Follow that? Now, what does this have to do with factorial? That's, what I'm telling you is that the number of ways that this could happen is 20 times 19 times 18, right? That's what I'm telling you. That's kind of like a factorial, isn't it? Kind of? Not really. Do you agree that this is 20 factorial over 17 factorial? Now, why? See, 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13, 12, blah, 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 right? But if I divide that by 17 factorial, I get 17 times 16 times 15 times 14, blah, 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 and then all of these are ones. And so all you're left with is that, right? Agree? So in general, watch, in general, let's say that I wanted to do this again. But let's say that I had, I don't know, instead of doing A, B, C, I'm just going to rank people, okay? And maybe I want to rank my students from first to second, all the way to like my kth favorite student, whatever it is, right? I have k different positions, right?
Yeah.
And let's say that I have n students. N students. Now we have to assume that the number of students is greater than the number of rankings that I'm going to have, although it could be the same. So maybe I want to just pick my top 3, or I want to pick my top 8, whatever, but no matter what, the ranking can't be bigger than the number of students I have. What would be the formula for this then? The number of ways that that could happen? Well, just like this, when I go to pick my first one, how many students do I have to choose from here? N of them, right? The next one, n minus 1, n minus 2, n minus 3, all the way down, right?
Yeah.
So following this pattern, can you tell me what this would be, the number of ways I could do that? N factorial on top, right?
Yeah.
Just like this one. But what's on the bottom? Not k factorial, n minus k factorial. So think about it. How many positions did we have in the previous problem? There were 3, right? Why did I put 17 on the bottom? Because I wanted to take away from 17 down, right? I wanted to take away all those and leave the 3 that were out front. So this would be n take away k factorial. That would be a general formula for the number of ways that you could maybe line up k people out of a group of n people. Yeah? Now you can start using this sort of factorial thing in probability of like lottery and things like that. But lottery gets a little bit tricky because with lottery, you know, the position you're in doesn't matter. Like when you pick the numbers in lottery, those numbers you pick, it doesn't matter. You don't have to get them in the correct order, do you? Like that first number you pick doesn't have to be the first number that's selected out of the little bubble machine or whatever that thing's doing, right? You just have to get those. So that their order doesn't matter. So things actually change. You have more chances. So anyway, the factorial is very, very useful in probability and statistics. But for us, we just need to know that n factorial is that. And I want to give you a property of it, one that you will see come into play. This one right here, this is a big one. N plus 1 factorial is equal to n plus 1 times n factorial. Okay, box that one because it's big time. We'll use that a lot. And let's just see if you can make sense out of it. What is the definition? What is the definition of n plus 1 factorial? You start out by multiplying n plus 1, right? And then what comes after that? You take away 1 from it, right? So what's next? N. And then what's after that? Take 1 away again, n minus 1. And then take 1 away again. And then that just continues down till you get to 1, right? Okay. Do you see that this right here is just n factorial? Right?
Yeah.
So I could rewrite n plus 1 factorial as n plus 1 times n factorial. So it's almost like you peel just one of the numbers off the front. Sometimes it's easier to see it if you do it with numbers. If I do 8 factorial, this is the same as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? But I can write that as 7 factorial. So it's almost like the 8 just peeled off the front, and then you've got the rest of the multiplication happening down there. You'll see. Stay tuned. We're just going to use that property later. We're going to have in something we're doing an n plus 1 factorial. I'm going to go straight to here, and then our n factorials are going to cancel with something, and it's going to be nice. All right. Let me see if you can simplify this. We've got, what, 30 minutes? I would like for you to take 2n plus 3 factorial over 2n minus 1 factorial. I'd like for you to rewrite this. I'm going to go get a drink. Y'all can work together on this. I'd like for you to rewrite that. And I'd like for you to rewrite it where there's no more factorials. Okay? All your factorials are gone. Okay? That's all I'm going to tell you. So, understand? You have to rewrite that. You're going to have stuff in there. You're going to have numbers and ends in there, but all your little exclamation points are gone. And do not just cancel the exclamation points. Those are not like numbers or variables. You can't. So, see if you can't figure out what's going on there. I'll be right back and go get a drink. Anybody need a drink? If you don't know what to do, I would just use the definition. Like write those out. What are they? What's the top? What's the bottom? Talk to each other. Yes? Think so? Or are you being sarcastic?
Is this like somewhat it, maybe?
Mm-hmm. Yep. Can I give you a hint? Okay, so what if I gave you 12 factorial over 7 factorial? Okay, let's say I gave you that. 12 is bigger than 7, right?
Yeah.
Over here, which is bigger, the numerator or denominator? 2n plus 3 should be bigger than 2n minus 3, right?
Yeah.
Okay, so on this, if I were to write this, this would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times blah, 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 all the way down. And then this one would be 7 times 6 times 5 times 4, right, all the way down.
Yeah.
And then starting here, they would start canceling, right?
Yeah.
And you would be left with this, right? Okay, same sort of thing happens here. Maybe I need to do it. What would the first piece of this one be? 2n plus 3. Okay, what's the one right next to it? 2n plus 2. Next one. 2n plus 1. Right? How far do I want to go? I want to go all the way till I get down to this, don't I? Okay, so this is 2n, next one, right? Then 2n minus 1. And then it would be like 2n minus 2, and that would keep going, wouldn't it?
Yeah.
Everything from here down is what? 2n minus 1 factorial. That's what that is, right?
Yeah.
And then on the bottom, you have 2n minus 1 factorial. So what you've done is you've peeled off enough of these to make the top part match the bottom part, and then you can cancel these out completely. And then you no longer have factorials. Does that make sense? Okay. I didn't intend on having you work on that, but I really need a drink. I never drink soda, and I don't know why I got that, but I never really get headaches like this either. I have, yeah, I've drank water. So far, are we good in terms of this? Y'all feel comfortable? Somewhat? Yeah, I know what you're saying. All right. Let's look at some sequences visually. Let's make up a sequence that we're just going to make up on our own. How about this? I'm going to do a sequence, let me do n plus 1 over n squared plus 1. I'm just making this up out of nowhere. All right? What would this sequence look like? So what would my first term of my sequence be? So plug 1 in, right?
Yeah.
2 over 2, so 1. What would my second number be? So you're plugging in 2, right? So you get 3 over 5, 3/5. And then next one, 4/10, right? I need to reduce that, wouldn't I?
Yeah.
But who cares? Wait, is that 10? Yeah, squared plus 1. And then my fourth, let's do one more. Fourth one would be 5 over 17, and then dot, dot, dot forever, right? That's my sequence. All right, let's visualize this. Remember when I did earlier, I did the dots? I'm going to do the same thing. It was n plus 1 over n squared plus 1. There it is. All right, there's my sequence. If I visualize it, if I plug in 1, I'm up here at 1. That's 1 up there. If I plug in 2, I'm here, whatever it was. And then 3. Look at this sequence of dots. The red curve is not the sequence, right? The black dots are the sequence. But do you see what's happening as you kind of let n go to infinity? As n goes to infinity, the sequence is doing what? Going closer to 0, isn't it? So we could probably say that this sequence, as n goes to infinity, like if we took the limit as n went to infinity of that sequence n plus 1 over n squared plus 1, it appears that the answer is what? 0, right? It appears that it's 0. As you go out further, these get smaller. Does that make sense visually?
Yeah.
Now, how would we do that? How would we do that without the picture? Like if we didn't have the picture, how do we know that as we let n get big, that this thing goes to 0? Okay, so that the bottom, you're saying the bottom increases at a faster rate than the top? I agree with you, but I can give you a sequence that I don't think you'll be able to do that, where you might have trouble. I know I could, so if we have to do something mechanically, how would we handle it? What's that? L'Hopital, right? You remember L'Hopital? Okay. What did L'Hopital say? That if you take a limit of something and you get infinity over infinity, then you can just take the derivative on top and bottom, right? Okay, we have a major problem with this though, because when you take a derivative, you're finding the slope of a tangent line, aren't you? Of a function. This black dots all over the page is not a function. How can you talk about the slope of a tangent line at a single point, right? Like if I'm at a single point and there's no points anywhere near it, how can I talk about a tangent line? There's nothing next to it. Does that make sense? You can't take derivatives of sequences. You can't, because they're not functions. That's one of the first things that you need when we're talking about derivatives. You need to be able to somehow come in from one side, take a limit, and come in from both directions. You can't do that on a dot. Does that make sense? So L'Hopital is going to kind of fail us at this point. Don't worry, it'll come back. It'll come back. We have a way of saving it. I'm just trying to get you to see right now that visually we can start talking about what these sequences do as we go to infinity. All right? Let's do another one. How about, I'll do it over here so we can see it. How about the sequence cosine n over e to the n? So what's going to happen on top there? We start plugging in numbers. It'll be fluctuating, right? Because we know cosine is going to go like that, and as we plug in different integer values, it'll be like speckled all over the place, right? Let me just actually put cosine n in, just so we can see what cosine n by itself looks like. So that's cosine n. And please make note that the red curve is not the sequence. The black is the sequence. So what we're getting is a bunch of speckles everywhere as we move down, right? But we want to take that and divide that by e to the n. So look what happened there. So what happened? It tries to be cosine, right? It tries to be cosine, but then the denominator, e to the n, starts getting huge really fast. And so as it tries to speckle, the denominator gets huge and makes all those numbers really small. So it's actually trying to fluctuate here, but it's getting smushed down because the numbers get smaller. So it looks like that sequence also converges to 0, doesn't it? All right, so we have a definition now, all right? Let me take this off of here. A sequence A sub n is said to have a limit, capital L, if the limit as n goes to infinity of A sub n equals L. If the limit exists, we say A sub n converges. We've heard that terminology before, haven't we? But when we used converges before, it was when we were talking about improper integrals, right? If the limit exists, we say A sub n converges. Otherwise, we would say what? Otherwise, A sub n diverges. If A sub n converges, we write A sub n with an arrow to L. That's another way of saying that our sequence converges to L. Guess what we're going to be focusing a lot of our attention on now? I'm going to be giving you sequences and asking you if they converge. Right? That's what I'm going to be doing. So here's our first example. Find the limit as n goes to infinity of n plus 1 over 3n plus 2. And remember, for right now, L'Hopital's off the table. What do you think that converges to? Let's see if you remember this from college, or not college algebra, Cal 1. When we let n go to infinity, the top becomes infinite, doesn't it? The bottom becomes infinite. L'Hopital's off the table, sorry, can't use it. But we can still use algebra. And the algebra we can use here is to multiply the top and bottom by 1 over n. And the reason I'm doing that is what I looked at was the highest power of n that I saw in the denominator. I had n to the first power. Do y'all remember ever seeing that in Cal 1? This was a technique that we used before we learned L'Hopital's rule. Look at the highest power of the denominator, multiply by 1 over it on the top and bottom. And something nice happens here. So what happens if I multiply that through and multiply that through? Yeah, so we get 1 over n times n, which gives us 1. Then 1 over n times 1, which gives us 1 over n. And then over here, what happens on that multiplication? What do I get there? What is it? 3. And then plus, and then this one to this one, 2 over n. Now let n go to infinity. What happens when n goes to infinity now? That goes to 0, right? And this one goes to 0. And so all you're left with is 1/3. So if I were to graph this sequence, these dots, what I can tell you is that they would converge to 1/3. They would start heading towards 1/3. And we could see that if we wanted to. And plus 1 over 3n plus 2. There we go. So you see, I have it here. We're going towards 1/3. So we start plugging in. Here come my dots, dot, 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 and these are getting closer to 1/3. How about this sequence? What's the limit as n goes to infinity of sine n? It's not going to exist because this would also look like, this. It would try and be a sine curve, right? But it's just a bunch of these weird speckles all over the place. Is that headed towards one value? It's not, right? So this limit would not exist. So we would say that this sequence, the sequence a sub n is sine n. That sequence is what? It diverges, right? That diverges. The sequence diverges. Or you could say it's divergent. What about this sequence? Is that convergent or divergent? Divergent? Why do you think? It just keeps switching back and forth, right? This is the one that goes, what, -1, 1, -1, 1. Is that headed to anything in particular? No. So that would be divergent. How about this one? A sub n equals n. Does that converge or diverge? This is the one that did what? What was it? 1, 2, 3, 4, 5. Is that headed to one thing? No, it's headed to infinity, isn't it? But in order to say that it converges, it has to go to some L, and that L needs to be a number, a real number, not infinity. Diverges. How about this one? One half to the n. Does that converge or diverge? If you have trouble, write out the sequence. Plug in 1, you get 1/2. What do you get next? 1/4. What do you get next? 1/8. You just keep on raising it to bigger and bigger powers. So what's happening here? The numerator is always 1, right? The denominator keeps getting bigger. So that ratio is going to squeeze down to nothing, right? So this limit right here converges, that converges to 0, doesn't it? So I put the arrow there to say that this converges to 0. How about this one? Do you remember we got this sequence earlier? Didn't we have that earlier? Negative 2/3 to the n? Does that converge or diverge? It is switching signs. Is that enough for me to say divergent, though? Let's write them out. What were they when we wrote them out? It was negative 2/3, right? And then when we plug in 2, we get 4/9, negative 8 27ths. Is that approaching 0? Is it approaching 1? This one's a little bit more troublesome, isn't it? You feel like it is? Why?
Even though the signs are still alternating,
Mm-hmm.
the signs are getting closer and closer and closer and closer and closer.
They're get. So if you're telling me if I ignore the signs, these numbers are getting smaller.
Yeah.
Yes? They're getting closer to 0? I think I agree, but I'm not convinced why.
Like, I don't know, like what comes to my head is if you picture just the negatives and just the positives, they're both, so if your x right here, they're both going like this.
We need to establish something before we can proceed. Let's say that we have a number x. Suppose the absolute value of x is less than 1. Okay, so let's say we have a number that's less than 1, the absolute value. So on a number line, that number is, here's 0, here's 1, here's negative 1. Our number is coming from somewhere in here, okay? Then, what is the relationship between x and x squared? Which one's bigger? So if you take a number and you, let's do this. Let's take their absolute values just to make this simple. Which one is bigger? I'm not getting a resounding, this one's bigger? Okay, yeah, so take an example. Take any number you want in here, right? Like a half, right? What happens if you square it? It's a 4th, right? Which is smaller. That would work for any number you pick in here. Any number. Anything in here. If you take it and square it, it gets smaller. Normally we think when you square something it gets bigger, right? But if the number is between negative 1 and 1 and you square it, you're looking at that fraction getting smaller. So the relationship here is that this is bigger than this, right? Now, what would happen if we then again raise that to another power? So what would happen if I do 1/2 cubed? That'd be even smaller than 1/2 squared, wouldn't it? So that would be smaller. And then what about 1 to the 4th power? Even smaller and smaller and smaller. So what's happening here is that they're heading towards 0. What I'm trying to get you to see here is that if we just ignore the negative signs here, this number right here is between -1 and 1. So as we raise it to bigger powers, it gets smaller and it heads to 0. The fact that it's switching signs doesn't matter. Let's look at the graph of it. There it is. Now, it was an alternating sequence, wasn't it? So it was switching. Maybe it started negative, right? Or I don't care. And then it went positive, negative, positive, but they're getting smaller. And they're headed towards 0. So that's just something we have to remember. If we ever have a number that's less than 1, we raise it to bigger and bigger powers, that goes to 0. All right, I think that's probably a good place to stop. For your homework for tonight, if you want to start working out of this section, I mean, honestly, 5 through 8, and that's it. Page 434. 5 through 8. Because the rest of the problems are asking you to talk about convergence or divergence of a sequence, but I haven't shown you everything yet. We still have a lot of other things to talk about. These problems, they give you a sequence and they ask you to come up with a formula. Okay? Yes? Yes. Did I ever turn my thing on? Yes, I did. You were getting speeches? Oh, yeah.